As with so many differential equations, this one arises from realistic physical circumstances. We're told that the temperature of an object is assumed to decrease at a rate that is proportional to the temperature difference between the object and its surroundings. If the temperature of the surroundings is 25 degrees C, a model for the temperature theta of the object after time t in minutes is given by, and this is the equation we're given, d theta by dt, that's the rate of change of temperature, and remember it's a decrease, minus k into theta minus 25, where of course we're assuming theta starts at some temperature greater than room temperature, where k is a constant. Now, the first thing to look for in any first order differential equation is, can I solve it by separation of variables? If so, that is definitely the way to do it. And I think you can see that this one is very obviously solved by separation of variables, because simply rearranging it, if I take d theta divided by theta minus 25, that's equal to minus k dt, and the left hand side is purely a function of theta and the right hand side is purely a function of t, so we can integrate both sides independently. And these are very straightforward integrations to perform. On the left hand side we have the natural log of theta minus 25, and on the right hand side we have minus kt plus some unknown constant of integration. So once we've got this equation, the obvious way to get it into the form which we're asked to show, part A, is show that the general solution of this first order equation is given by theta equals a e to the minus kt plus 25, where a is a constant, is to take exponentials of both sides. So taking the exponential of the log, of course, just gives us theta minus 25 on the left hand side, and that is equal to e to the minus kt plus c on the right hand side. This is slightly deceptive. A lot of people slip up again with the algebraic manipulations here. So let me write this very explicitly, that this is e to the minus kt times e to the c. That's another way of writing the right hand side, and that's ae to the minus kt, where a is another unknown constant which is equal to e to the c. So that's a simple manipulation, and following that, of course, theta, I can add 25 to both sides of the equation, is ae to the minus kt plus 25 as required. Again, we're assuming that everything is in degrees c. So we're now given that the boundary conditions are that theta is 75 degrees C at t equals 0 and 60 degrees C at t equals 5, where t is in minutes, and we're asked to find the values of a and k and giving them to three significant figures. So first of all, let's associate the theta is 75 degrees C with t equals 0. So 75 is equal to a e to the 0, which is of course a, plus 25. So that immediately, straight away, trivially gives us a is equal to 50 degrees centigrade. So theta is equal to 50 e to the minus kt plus 25. So the other boundary condition we're given is that theta is equal to 60 degrees C at t is equal to 5 minutes. I'll put the units in explicitly here. I won't bother putting the units in each equation as we go along. So let's pop that in, that 60 is now equal to 50 e to the minus 5k plus 25, and that will determine k for us. Well, how does it determine k? We quickly rearrange the equation to give us 50 e to the minus 5k is equal to 35. which is likewise e to the minus 5k is 0.7, and taking logarithms of both sides, we have minus 5k is equal to the logarithm of 0.7, so k is equal to minus the log of 0.7 divided by 5, which is, we're asked to give it to three significant figures, 0.0713 minutes to the minus 1. Of course, kt is dimensionless, and if t is in minutes, we have to have the units of k in inverse minutes. The last part is, again, it's getting at the actual physics of the problem underlying the mathematics. We're asked to explain why the model breaks down when trying to calculate the time the object would take to reach 25 degrees C. Well, the problem is that mathematically, if you chuck theta equals 25 into the equation, theta equals 50 e to the minus 0.0713 t plus 25, then that gives you that 50 e to the minus 0.0713 t is equal to 0. And that's only true for t tending to infinity. And we could have said that directly without probably doing that little bit of maths. So what the model's suggesting, remember a mathematical model is only a model of a physical process, is suggesting it's going to take an infinite amount of time for the object to cool to the temperature of surroundings, which is physically not correct.